Today we're going to be looking at problem 3439, reschedule meetings for maximum free time 1. So let's get into it. You're given an integer event time, which is the duration of the event. It's going to be our upper bound, so starting from 0 up to event time. They also give us two arrays, start time and end time. Each one is going to be length n, so we know they're the same size. They represent the start and end time of n non-overlapping meetings, and then those indexes are going to be the ith meeting, and then respectively the start and end time. We're able to reschedule at most k meetings. We can move the start time, but we can't change the duration, and we also have to keep the same order, and they can't overlap. So our goal is to return the maximum amount of free time possible after rearranging those meetings. Now that we have an idea what the problem's asking for, let's take a look at the examples and see how they solved it. Hopefully that'll give us some insight. Example 1, so we see event time 5. That means that it's going to be from 0 to 5, and we can see that represented here on this graph, or line chart, I guess. K is equal to 1, which means we're able to move one meeting, and then start time and end time both have a length of 2, which means that we have 2 meetings, which we're also seeing here on this graph. The output is 2, so that means they were able to find the longest period is going to be equal to 2. And if we look at the gaps or the breaks that we currently have, there's 2. There's one between 0 and 1 of length 1, and then there's one between 2 and 3 also of length 1. So there's a couple ways that you could solve this. The way that they solved it is they moved moving A over 1, and then they instead moved it to 2 through 3, and that would move this gap over to the left and give us the 2 there. The other way you could solve it is if you move A over to the left from 0 to 1, and then 2 to 3 becomes the new gap. Either one's fine, either one works. Obviously, you're going to get the same outcome. So that's kind of showing here we're combining, when we move this meeting over, right, we're combining the gap to the left and the gap to the right. And for example, if this extended over, there was another space here. So just imagine this was, obviously it can't be like this, but if this was -1, just for the sake of this example, this gap would become 2. And then the optimal way to solve it would be moving A over to the right to conjoin B. And then again, we would have a gap of psi 3 because we're joining together 2 and 1 here, right? So these two gaps are getting merged and becoming a greater gap. So let's take a look and see what it would look like. A different example, one where the K is greater than 1. Taking a look at this problem I just drew, we can see we have 3 meetings here. K is now equal to 2. So we can move 2 meetings, and the gaps that currently exist on the page, there's one of length 2, one of length 1, and another one of length 2. As we can see, the event time would be equal to 8, and then for the sake of this, we don't need to list out the arrays, but they would be of length 3, because again, we have 3 meetings. The optimal way for us to solve this one is, there's a couple ways, but the way that we'll look at first is we would move this blue meeting over, right? So this would turn these two gaps into 1. So that would become a gap of 3. Now with the blue meeting moving over here, and then we had 2 ways. So we could either move the red all the way to the left, or we could move it all the way to the right. Either way, we would get the maximum gap size of 4, right? And if you're looking at it here, again, this pattern of when we move a meeting, we combine the gap to the left side and the right side, and we add them together. So every time we're moving one of the meetings, we're going to do that sum of the two sides. And keeping with that, if you notice here, our K is equal to 2, and we have added together 3 gaps. And if you look at the original example problem, the K is equal to 1. We also added together 2 breaks or gaps. And that's going to be consistent for any size k. So it will always be k plus 1. Again, because of that relationship I was just describing, where when you move a meeting, you're combining the left and the right. So now that we have a good idea of how we can solve for the longest break, we need to think of how can we get the gaps together in such a way that we can find the greatest k plus 1 period. And at this point, it should be relatively easy to identify that this is going to be a sliding window problem. Like I was just saying, we're going to have a window of size k plus 1. So really the only work left to do here is identify how we can get that array of gaps or breaks so that we can traverse it and try to find that biggest window. For us to identify the gaps, we can take advantage of the arrays that we see. So for the example 1 array, we have a start time of 1 and 3, and we have an end time of 2 and 5. And the way we can use this is the ending of the first array and the start of the next element in the starting array will tell us what the length of the gap is, right? Because if one of our meetings ends at 2 and the next meeting doesn't start until 3, we can identify that there's a space of 1. And this would continue. So if we look at example 2, let's see. So they have 0 to 9 as start time and end time as 1, 4, and 10. So the 0th meeting is an interesting case that we'll get to in a second. But jumping ahead, end time is 1, start time is 2. So we can identify there's a space of 1 in between them. Next, the end time of meeting 1 is 4, and the start time of the next meeting is 9. And we can identify a space of 5. So we can keep using that to identify these gaps, and that's how we'll actually create that array of gaps so that we can slide our window across it. Like I said, the 0th index is different, as is the last index. If you notice here, these are kind of by themselves, and the relationship we were talking about doesn't really apply to them. So in the examples that they provided, the last and first event are butted up against t equals 0 and t equals event time. But if you look at the constraints, which are not shown on the screen right now, there is no constraint saying that the meetings have to start or end at t equals 0 or t equals event time, respectively. So it is entirely possible that this could be t equals event time 11, and we could still have the same meeting ending at 10. That would be valid. That would be a valid example. So the way that we're going to handle that is the start time is as simple as the 0th index of start time, right? So in our array, if we have our array of breaks here, and then keeping with the example we were just working on, that 0th index is going to just be the 0th element of starting time. Because if you could imagine, if we had a meeting that started at 1 instead of 0, the break would begin here, right? So like we would actually have a break before the first meeting. And you can kind of think of the same thing for end time. So say we had an additional meeting from 3 to 4. The break here would be from the end time of the last element, which in this case is 4, minus event time, right? And we'll get another break here of size 1. Sorry, I meant event time minus end time. So if we look at, if we were to create the gaps for example 2, what that would look like is, again, the first gap is just going to be the 0th index of starting time, which is 0 for this one. And you can see there is no gap before the first meeting. Next, we will, again, look at the difference between the the first index of start time and the index before that in ending time, right? So it'll be, if this is I, the ending time we want to look like it is I minus 1. We'll get a gap of 1 there. Next, again, I becomes 2. We want to look at I minus 1 at ending time, and we'll get a gap of 5. And then lastly, that relationship we were just talking about, if we look at 10, so it'll be event time, which is 10, minus the last index of event time, which is also 10, and we have another gap of 0 here. And we want to find the largest window of size k plus 1. And in this case, k is equal to 1, so we'll just keep sliding the window over until we find the largest. We're trying to maximize the sum of that window, right? And here we can see it's 6, which lines up with the output for that example. So really the main way we want to approach this problem is we're going to use starting and end time, those arrays, to generate our array of gaps or breaks. And then once we have that array, we can simply slide our k plus window over it, and the problem just becomes a trivial sliding window. But the difficult part here is identifying that we can create that relationship of k plus 1 breaks being the answer. So now that we have an idea of how we want to approach this problem, we can go ahead and start coding it. So remember, the first thing we want to do is we want to create that array of breaks. And if you remember, the breaks, that list of breaks is going to be the length of the number of meetings plus 1, because we're going to have that break after the meeting. Sometimes it's going to be 0, but it does need to be there. So we can just do 0 times length of start time plus 1. So we'll initialize all of those breaks to 0, and then if it's greater than that, we'll update it. If not, it can stay at 0. So again, all those conjoined meetings are going to have breaks of 0. If you remember, that there are 2 special cases that we have to deal with before we can start using start time and end time to figure out the gaps between the meetings, and that is the first and last meetings. We need to see if there are any gaps before them, kind of like in this one, we can see that gap before the first meeting. On the examples, they don't have a meeting where there's a gap after the last meeting, but it is a possibility. So the way that we want to do this is breaks 0. So again, that's the first break before the first meeting. It's just going to be equal to start time 0. And the reason why is, for example here, whatever the start time index is, that will be the length of the break, because whenever we're starting that, any time before it is a break. Next is the gap after the last meeting, or the break after the last meeting. So it will be event time minus end time -1. So it's going to be the last index of end time minus the event time. So for here, we know it's 5. If, for example, it was 10 and the last meeting ended at 5, the difference of those two numbers is going to be that length of break. Okay, so now that we have the special cases taken care of, we can continue along iterating through. All of them will follow the same format. And if you remember, we can use the start time and then the end time of that -1 to get that break length. So for I in range, and we'll start at 1, and we're going to stop at start time, since we've already handled the first and last. So all we need to do is breaks I is equal to start time I minus end time I minus 1. And again, that's pretty intuitive. The start of this meeting, the gap between the previous is that end time I minus 1. So when the meeting before it ended, that will give us the gap, that difference there. So with that, we should have a fully populated array of all of our breaks, and we can start using our sliding window to find that max break window. So we'll create some variables here. So we want a variable to keep an eye on the max that we've seen so far. We need a variable to keep the max of that current window. And then we need a left pointer for the leftmost side of our window. I see a typo. Okay, so we'll do for right in range and then length of breaks, right? Because we want to slide all the way to the end. And when we're iterating through, the way it's going to work is we will add the break that we're currently at to our current window. So we'll do cur plus breaks of the current index. And then we need to check if our window is broken. And the way we can do that is, if you remember, the relationship here is, or not the relationship, but we're allowed to combine at most k plus 1 gaps or breaks. So it'll be while right minus left is greater than or equal to k plus 1, our window is now broken. And we'll reduce the leftmost break and slide it forward. That's the window sliding action here. So once we've ensured that our window is not broken, we can just do max free time equals max of what we've seen before and what we're holding there and what we currently have in our window. At that point, we have the max, like once this is iterated, we'll slide our window across our array of gaps. And then when we reach this point, we will have found the largest gap and we can simply return it. So if we run it, okay, end time, typos, love typos. I think that's all of them. So let's try one more time. Okay, great. That was test, so we'll submit it. And perfect. And you can see, well, I guess there's not enough accepted submissions. But anyways, hopefully you liked the video. Give me a like or leave a comment, maybe subscribe. And I'll see you in the next one.